So now we are discussing pipes in series topic. So let us solve a problem on that, how we use the methods that we just discussed to solve the problems. Now this is problem 8.9.1 from the textbook. Suppose we have in the figure 3 pipes are now connected. We have one pipe, this is second pipe, and then we have the third pipe. So the data is given, and it is stated that the total head loss, that is 6 meter between A and B. So it means that this head loss is given. This is given 6 meter. This is now given to us. And for the 3 pipes, the lengths are given, the diameters are given, and in this case, the friction factors are given. Clear? So now first, as we studied that we have 2 cases that we have studied. Now in this case, the total head loss is given, and we have to calculate the discharge. What we have to find out? We have to find out the discharge. So first you have to identify that this is which case. Clear? So this is case 2. If you remember, this is case 2, for which we have to calculate the discharge, and the total head loss is given. So now in that case, we have 2 methods. Either you apply the equivalent velocity head method in order to calculate the discharge, or we can also apply the equivalent length method. Clear? So first let us see, we apply the equivalent velocity head method. In that case, we already discussed that the equation is given by this form. So now essentially in this case, what we have done is that we have expressed the velocities of second pipe and third pipe in terms of V1. You can see here, in terms of V1, we have expressed the other velocities. That's why it is known as equivalent velocity head. So now in this formula, you can see that F is given, L is given, D is given, and so on. So just you need to put the values, and in this case, this HL, this is also given. Clear? 6 meter. This 6 meter which is given, that you put here, HL. So in this case, the only unknown is this V1. This V1 is unknown. So now we calculate, you plug in the values, and then we calculate that this V1 is equal to 0.63 meter per second. And then we already know that Q1 is equal to A1 into V1. So you plug in the values. So the discharge comes out to be 0.00317 cubic meter per second. So you can see that we can easily solve the problem. Clear? Now in this case, remember that we express V2, if you remember V2 and V3, that we express in terms of what? In terms of V1. So that is why in the whole equation, and that V1 is here. So that's why in the end, what we get? We get V1. That is why we are able to calculate V1. And then we can easily calculate Q1, which is the discharge through this pipe here, 1. So now we already know in this case that in this case Q1, that will be equal to Q2 equal to Q3. Clear? So once you calculate Q1, it is equal to Q2 equal to Q3. But if you proceed with V2, then it will be V2 here. You can calculate Q2, or you can express, clear, V2 and V1 in terms of V3. Then here you will calculate V3. This will be V3, and you can calculate Q3. Meaning to say is that it's not always that you will calculate V1 and then Q1 and so on. It can be V2, it can be V3, and so on if we have more pipes that are connected in series. So as a check, what you can do is that now V1 we have calculated, so you calculate V2. We can calculate easily now. You can just plug in the values, and V2 is this much. Now from Q2 is equal to A2 into V2, you calculate, and the discharge is 0.00317. You can compare this here, 0.00317, get the same result. Similarly, you can go for V3 and calculate Q3. You will get the same result. Clear? Now next we apply the equivalent length method. Let's see that we get this result of 3.17 liters per second or not. because we discussed that there are two methods that we can apply to solve this problem when the pipes are connected in series. For case 2, the head loss is given and we are required to calculate the discharge. So as I said that this much, the problem is sufficient. We already get the discharge, but we apply this second method to calculate that if we get this discharge or not. And as I said that in the eighth edition, for example, of the book, older editions of our textbook, you will find that they discuss the equivalent velocity head method and the equivalent method both. But now in the 10th edition, they do not discuss this method. Only just they discuss the equivalent velocity head method. But anyhow, we will apply both in order to see that we get the same result or not. Clear? And this is also for learning purpose. So in the equivalent method, what we do is that we have to select one of the pipes, either pipe 1 or pipe 2 or pipe 3, any one for the given pipes connected in series. That can be selected as the effective pipe. Clear? And what we will do is that we will calculate the effective lengths for all the pipes in terms of that selected pipe as effective pipe. So let us proceed how we do it. We already discussed and derived this equation that we can calculate the effective length for any other pipe, clear, which will have the same head loss for the same discharge. So now in this case, you plug in the values. Everything is known in this case, clear, because we select pipe 1 as effective pipe. So this effective pipe will take all the properties of pipe 1. So that's why when you put the values, then the effective length of pipe 1 will be 150 meter. What is the length of pipe 1? If I go back to the table, what is the length of pipe 1? It is 150 meter. Because we select pipe 1 to be effective pipe, what should be its length? That will cause the same discharge Q1 for the same head loss HL1. So its length comes out to be what? Its length comes out to be 150 meter. Because pipe 1 is selected as effective pipe, its length remains the same as 150 meter. This is the concept of effective pipe. So pipe 1 is now effective pipe, so its length remains the same as 150 meter. Clear? Next, we calculate the effective length for pipe 2. Now in that case, you plug in the values, because we know all the values for pipe 2 and effective pipe. And effective pipe will get all the values from pipe 1, because this we declare pipe 1 as effective pipe. So it means that FE will be equal to F1, DE will be equal to D1, and L1 will be equal to LE. This is what essentially we are doing here. Clear? So now when you plug in the values, then in that case, this LE2 effective length, that comes out to be 703.16 meter. This should be the length of the pipe in order to cause the same head loss as that of the pipe 2. If you compare here, we go back to the table and you look here, now the effective length of pipe 2 is no longer 60 meter, because now effective length of pipe 1 is 150 meter. So if you want to replace pipe 2 by effective pipe, which is now selected as pipe 1, then its length should be not 60 meter. Its length should be how much? Its length should be 703.16 meter. Clear? Then it will be the equivalent length. This is how the equivalent length concept comes. It is not equal, but the equivalent length. If pipe 1, if we want to replace C703.16, if we want to replace what? This pipe 2 here, you want to replace this pipe 2 with effective pipe length, that will cause the same head loss as the pipe 2. And the pipe, effective pipe we select as pipe 1. What should be the length? What should be the length here of the effective pipe? That will cause the same head loss as this pipe 2. So that should not be 60 meter. It should be this much here. 703.16 meter. Next, we calculate LE3. So for LE3, you plug in the values for the effective pipe and the LE, the pipe 3. So you will get the length is 535.42 meter. So now what will be the total length of the effective pipe? That effective pipe and we calculated the effective length. Clear? That pipe 1 should have this effective length of 1388.58 meter. Then in that case, it will cause the same head loss as the 3 different diameter, different length pipes together. So in that case, now this HL is known. Clear? LE, we are able to calculate. DE and FE are known. This is known. Only unknown is this VE square. So now in this case, you plug in the values, and then from here, we can calculate this VE. And now from here, we can calculate the discharge. So this is AE. This is essentially area of the first pipe, because the first pipe we selected as the effective pipe, 0.08. From where it comes, you can see here in the table. Here this is 80 millimeter. So keep the units consistent. So this is how these values come. This here. So now we are able to calculate the discharge. So now from here, the discharge comes out to be 0.00317 cubic meter per second. Now we get the result. This was what was required. That we calculate the discharge, and this one was given as 6 meter here. You can see here, this one was given. So now you can see that we apply the equivalent length method, and we get the same result as we applied the equivalent velocity head method. So that is why when we solve this problem, you apply the equivalent velocity head method or you apply the equivalent length method, you get the same result. Clear? So in this case, just remember, we express this pipe 1 in terms to be the effective pipe. You can select pipe 2. We have pipe 2 that can be selected as effective pipe. Similarly, you can select pipe 3 that can be selected as the effective pipe. So any one of the pipe can be selected as the effective pipe, and then we calculate the equivalent lengths for all the other pipes. And then this is how we proceed to calculate the discharge. This is the equivalent length method. Now in the 10th edition of the textbook, this method is no longer given. In the older edition, it is given, but we need to learn how this method is an option available beside the first method to solve pipes in series problems. Clear? So now in this case, let us solve a problem. Here we have pipes that are connected in parallel, and these are the lengths, pipe lengths given, and the diameters are given in this case. So this is case 1 problem. Clear? Because in case 1, we have to calculate the total head loss. So this is the case 1 problem. In this case, now also note that the friction factor is unknown. You see F1, F2, F3 are not given. The discharge is given 7 liters per second, but we have to calculate the total head loss between this point here, this point A, and this point B. What is the total head loss? And the flow in each pipe. That we can calculate, the total flow is given here. Now, in this case, you see that we do not have F1 value. In this case, F1. Similarly, we have F2 and we have F3. So these values are not given. So you will see that essentially it will become a trial and error procedure. So how to proceed and solve this problem? So we are given the temperature. Because we have to calculate the F values and compare with the assumed values, we will need to calculate the Reynolds number. So that's why from the figure A2 for crude oil, this is in appendix. Appendix, you have figure A2 end of the book. So at 50 degrees C, this is the kinematic viscosity value. Clear? This because we are given that in these pipes, what is flowing? We have crude oil. It's not water. We have crude oil. So for that, you have to read the value from figure A2, which is given in the appendix of the book. So the kinematic viscosity is now this much. So for also, it is stated that the pipe is copper tubing. You can see here, it is mentioned that the pipe is, material is copper tubing. So we need to calculate the value of E. And we already discussed that there is a table given in the textbook chapter 8, table 8.1. It gives the E values for the different pipe material. So you will get the value from there. Now we already know that the same head loss will occur for all the pipes when the pipes are connected in parallel. HL1, this is what? This is your HL1. And this is your HL2. And this is HL3. Clear? So we already defined these equations in the previous slide, that we can express V2 in terms of V1 and also V3 in terms of V1. This we already discussed. Now what we have to do is that this F1, F2 and F3, since they are not given, so we have to assume the value of F. You will start from some minimum values. Clear? So now in the first trial, what we assume is, this is for simplicity. You can assume different values, but let us assume F are same for all pipes. This we make an assumption as part of the first trial. This is an assumption. You can start with the first trial by assuming different F values for all the 3 pipes. But this is just for simplicity. What we do is that assumes F values same for all the 3 pipes. Clear? In this case, you can see that the pipe, the different flow conditions. So we just assume that F are the same for all pipes. So in that case, F1 equal to F2 equal to F3. So that cancel out and it simplifies the equation. So now we can calculate V2 in terms of V1 here. This is now given and this is given. Now we are given the total discharge Q. Clear? So that is 0.007. You just keep the units consistent. And in terms of this pipe 1 here, so we can calculate this V1. From here, we can calculate V1. What is stated here in the problem? That suppose that in figure pipe 1 is this much, pipe 2 is this much, pipe 3 is this much. The length and the diameter, clear, is flowing 7 liters per second. So that's why we write down here that 7 liters per second. Keep the units consistent. And now we can calculate V1. If you see here, only unknown is V1. So now we are able to calculate V1. Now from this, we can calculate the Reynolds number, which will be D1 V1 into in here. So this V1 value, what you can do is that you can put this value here V1. That you can put here to calculate V2. And similarly, you can put this V1 here to calculate V3. We can now calculate V2 and V3. So before we calculate the discharges, we have to make sure, because that discharges may not be the correct one, because we use the F values we assumed. So that is why what we do is we calculate the Reynolds number R1. Now everything is known. We calculate the Reynolds number R2 and we calculate the Reynolds number R3. You can see all the 3 Reynolds numbers shows that the flows in the pipes are turbulent flows greater than 2000, which is the critical value. So now for R values, flows are turbulent. Now similarly, we can calculate E1 by D. E is given same for the material pipe is same, but the diameter is different. So the relative roughness is this for the 3 pipes that are connected in parallel. So now in this case, for these R1 and E by D, you will go to the Moody's chart, or you can use the Colebrook equation or Holland equation, and you will calculate the F values. So now using, let's say, the Holland equation, we calculate that the F1 value is 0.037, F2 is 0.0296, and F3 is 0.0234. Now you can see that what we assume that the 3 F values should be the same. But now when we calculate, they are not the same. You can see they are different. So it means that our initial assumption is incorrect. Now next we go for the second trial. We will continue with the trial unless and until the calculated values of the friction factors becomes the same as the initial values of the friction factor. So now for the second trial, we will calculate V2 and V3. Clear is given like this here. Why? You can see here in this case, it is different. You see this equation here, V2 is equal to 1.095, but in here V2 is equal to 1.225 V1. Why this different? Because now we are using these values, F1, F2 and F3 for the second trial. Previously what we did, we assume same F values, so that cancel out and we get these as simplified expressions. Now that we put the values of F1, F2 and F3, so now these are the expressions that we get for the velocity V2 and V3 in terms of V1. So again, we plug in the values in this equation as we did before. And now from here, the only unknown is V1. So we calculate V1, which is now equal to 0.835. Previously, it was how much? 1.017 meter per second. Now this comes out to be 0.835. And this value, now we can put here. Put this value here. And similarly, put this value here. You will calculate V2 and V3. So based on that, again, now we calculate the Reynolds number. So we already have this E by D1, E by D2, and E by D3. So again, we calculate using the Holland equation or Moody's diagram. We calculate F1, F2, and F3. Now you can see here, what is F1? Our F1, this is how much? Our F1 is how much? 0.037, and this comes out to be 0.0393. Now look here, F2 that we assume, that is 0.0296. What is F2 here? 0.0303. Not same. F3 0.0234, but it comes out to be 0.033, which is a bit close. So now we go for the second trial, third trial. In the third trial, we will start with these values as our initial assumption. Clear? And again, we calculate V2 and V3 in terms of V1. And again, we plug in the values in this equation here, and we calculate V1. Similarly, we can calculate V2 and V3. And again, we calculate the Reynolds number, R1, R2, and R3. And you apply again the Holland equation to calculate F1, F2, and F3. Now you can compare these values with the assumed values. These will be close enough. So these values are now close enough. So that is why we can stop the iterative process. So now we can calculate the discharge. So your Q1, that is this much. Similarly, we can calculate Q2 because now we know A1 and we know V1. We can calculate Q1. We know V2 and we know A2. We can calculate Q2. And so on, we can calculate Q3 to be this much. Clear? These are now the correct values because we use the correct values of F. And head loss we can easily calculate here. So this comes out to be 5.99 meter. If you calculate for pipe 1, this is 5.99 meter. And since we stated that the same head loss will occur for all the 3 pipes, so as a check, you can calculate HL2 for the second pipe for the given calculations, and you can calculate HL3 for the pipe 3. So all the 3 pipes are connected in parallel, the same head loss will occur. You can see 5.99, these values are close enough. So this is how we solve the problem when the pipes are connected in parallel. So if F values are given, then you can directly solve the problem. But if friction factor values are not given in the problem, what you have to do is that initially you have to assume the values of F, and then you have to calculate the values of F. And the trial and error procedure, it will continue unless and until the calculated values of F, they exactly match the assumed values. Then the trial and error procedure will terminate and you will get your final solution.